semester with this content. I think that this may be the last chapter we do, and we'll just do a review for the final next week, but no new content. And then I'll probably do that Tuesday. Final will go up Wednesday, and then you'll have till the following Wednesday to submit it. That way you get a full week to work and to have that submission in. So does that sound okay schedule-wise? Or are people good with that?
Sounds great.
Okay.
Randy.
Yep.
Because if, like I said, if we were actually meeting in class and having a exam in class and things like that, I would have wanted to have one more chapter in, because we would have been able to do that by just all hands-on stuff. But at this point, it would just be like kind of how the other vocabulary terms were when I just had you basically write definitions from your textbook, and I don't feel like that's necessarily learning. So despite the fact that I'd love to teach this content, I don't really think that you guys would get a lot out of it the way that we're working with these things now. So I think we'll just end here. Do you take any other lean classes, or do you do any other lean work in your program? Or is it an elective that you can take, an actual lean class?
Not that I know of.
It's one of those things where this textbook, and I've taught other classes at Purdue that were like this, where, you know, when you talk about operations management, you're talking about kind of the 30,000 foot view, right? But all of these things that we cover are actually entire courses. So doing inventory planning is an entire class on its own. Doing MRP work and ERP work is an entire class on its own that has a lab that we spend all of our time doing SAP so that you're actually working in an ERP. Doing lean is an entire class on its own. And at Purdue, they actually offer lean and then Six Sigma, where you actually earn your Six Sigma green belt through that class as well. So these are topics that they're condensing into a chapter to try to give an overview. But if you wanted to really do well in any of these subjects, you would need to study them in much more detail. So I'm trying to highlight the things that kind of give that big picture framework, understanding that in reality, you know, this does not make you an expert in this. You would need to study it at much deeper levels to really have an understanding of how this works. But if you go into manufacturing and you're working on the line, like, you will very quickly know all the product families that you're associated with. You'll know the inventory management practices with the products you're associated with. You'll know the lean techniques that are being used in your manufacturing work cell. Like, as soon as you hit a job situation that's employing any of these, you'll quickly learn those techniques that are specific to that. And so hopefully this gives you a little bit of an awareness of why they're used and why they're important, and just understand that this is a really quick brush over a topic that's actually quite complex. And I think I said in the lecture, you know, people that work on MRP systems, ERPs, we had, so when I worked for Hoffman LaRoche, we were manufacturing 24/7, 365. And in that situation, we had a team of at least half a dozen people that solely worked on the pharmaceutical raw materials. There were another group of purchasing agents that worked on the inventory for all the packaging components. And there was another group of people that worked on all the inventory for any of the liquid products. So that was just like pills and tablets, but liquids was a whole different group altogether. So all in all, our inventory management staff was probably 20, 25 people whose full-time jobs day in and day out was just doing inventory management. And our textbook presents it in a single chapter. So just to give you some scope, that this is a a big task. It's a really critical task because you cannot run equipment if you don't have the product to run it. And that's the main point here, that you have to have all of the components in place on time before you ever start manufacturing that first good. And so, you know, if you went to AZIP and they had no crust whatsoever, it doesn't matter how many other parts of the pizza that they have. It doesn't matter how many people they have working there. It doesn't matter how great their oven is functioning. If they don't have crust, you can't even get started, right? So that's kind of what MRP is looking at, is saying, you know, when our customer places an order, the assumption is that we have everything we need, and that the equipment is working, and that we have all the people in the right places at the right time, and all of this is going to come together, and we're going to make a good product. We're not going to screw it up, which we know from previous chapters is also a pretty big task. So the scope of this is really, really significant, even though the specific, you know, like technique we're going to do now is kind of an oversimplification of that. And so this exercise that you're doing and the one that'll be in your homework, there'll be a similar one on the exam. They'll all basically look exactly the same, but it's just getting across the idea that you have multiple components that go into these sub-assemblies, and these sub-assemblies come together to be final products. And so if you think from an inventory management, I need to have all of that material. If you think from a human resources perspective, I need all the people to run the equipment. And then you think from a maintenance perspective, I need all of the equipment to actually be running in good condition. Then you think from a quality perspective, well, I need all that product to be manufactured right the first time. And so all of these pieces come together in something that seems pretty straightforward. So this is called a product tree diagram. And it's because like you have a root system at the bottom, and then you have branches, and then off of those branches you have sub branches, and then you have these little leaves. So it's a tree diagram. These are very useful in breaking down large complex entities into individual components. And so we read it from the bottom up because this is where you would actually start. So the product P2 is what's being shipped out the door, but all the way down here, those raw materials that are going to be processed and come together in some way to make the sub-assemblies that go into P2. And so what we have here is the numbers in parentheses tell us how many you need of each of those individual items so that you could actually produce these parts. So the customer requirements are in bold at the top of the table here. They want 2,000 of P2. And so to make 2,000 of P2, we need to start with the idea that we need sub-assemblies 3 and sub-assembly 4. Now we need one of each of those to come together. So we're going to ignore quality for a minute. We're going to assume perfect quality, which is a terrible assumption, but in the real world we build in extra units. But just to get out 2,000 perfect units, I would need 2,000 of sub-assembly 3 and 2,000 of sub-assembly 4, because I need one of each of those to come together to make P2. So I look at sub-assembly 3, and I know that I need 2,000 total, but I'm gonna zoom. Let's see if I can zoom at this point. There we go. Is that still pretty clear for you guys? Thumbs up or something?
Yes.
Thank you, Justin. I appreciate it. Okay, so we need 2,000 of subassembly 3, but I already have 500. So what do I actually require? It's that 2,000 minus the 500. So I need 1,500 of subassembly 3. That's an important number for me to know, because when I look at all of the materials required to make subassembly 3, I need one of them 4, I only need a half of them 6, I need 1 of C4 and 2 of C6 all to come together for subassembly 3. But I'm not basing it off the 2,000 parts that I need for P2. I'm basing it off the fact that I need 1,500 because I already have 500 subassemblies 3. So they already include all of those parts, right? So it's important to remember that I'm working off of these subassembly components and I don't just write 2,000 of each of those. So for the next one, subassembly 4, I have 200 on hand. So again, I've got 2,000 minus 200, and so that equals 1,800. Now, on your paper, I see it's kind of blurry. On your paper, you don't have to write the math. You could just write the actual number. So this one would actually just say 1,500. This one would actually say 1,800. I'm just doing the math to show that that's the process to get there. Now, I am going to jump in because now that I know what I need for my subassemblies, I have to work from the bottom up. Because when I look at this, I have to keep in mind that for every P2, for example, starting down here, I have 1 material 7 and then 2 of component 7 that go into that. Well, for every component 7, I have 1 of material 7, but I need 2 component 7s for every P2. So what does that mean? Well, that means for material 7, I'm looking at not just the 2,000 that are required to make P2 because I need 2,000 parts, but how many do I actually need? Because P2 requires 2 of C7. So how many material 7 do I actually need? I actually need 4,000, right? So if I need 2,000 of P2, but it takes 2 of C7 for every 1 of P2, that means C7, I need to have 4,000 total. Well, it takes 1 of M7 to go into C7, so that means I have 4,000 of M7 as well. So for C7, I have 0 on hand. C7, oh, no, sorry, I have 50 on hand. So C7, I need 4,000 of those total, minus the 50 that I already have on hand. And so that means I need 3,950. And for component 7, it uses material 7. Now, I already have 200 on hand, but how many do I need? I need 3,950. So that's 3,950 minus 200. And so that equals 3,750. So you have to look at your tree and see how many that you need in total so that you know as you move forward what do you actually need. So I'm going from the bottom up and the top down simultaneously. I know I need 2,000 of P2. To get 2,000 of P2, I actually need 4,000 of C7. To get 4,000 of C7, I need 4,000 of M7. But because I have on-hand inventory, I already have 50 on-hand C7. So that takes away 50 of those 4,000. So I only need 3,950 of C7 left over, and I need 1 of M7 for every C7 that I make. So then I only need 3,950 of M7, but I have 200 on hand, so I subtract that 200, and that gives me 3,750. Does that make sense? Because I'm kind of having to keep in mind the grand total that I need at the top, and then the individual totals of each individual component, but I have to do that with respect of how many units I already have on hand. Does that make sense for everybody? So I did that one. I'm going to check these off because these are done, right? Okay, so let's go back and look at subassembly 3. So at subassembly 3, I have 1 for every one of P2. So when I have 1 of every one for P2, I only need 2,000 of subassembly 3. But I had 500 on hand, so that means the starting point for all of these submaterials isn't 2,000, it's 1,500. So to make subassembly 3, I need 1 of C4 and I need 2 of C6. So for C4, if I need 1,500 of subassembly 3, that means I need 1,500 of C4. So I go down to C4 on my list, and I have 0 units on hand, and so I have 1,500 because there's no on-hand inventory that I need to take care of. Now, I look over and I see C6. I have 2, I need 2 of every item C6 to make 1 of S3. So I need 1,500 S3, but that multiplied by 2 means I actually need 3,000 of C6. So I come down to C6 and I look and I have 0 on hand, so I need 3,000 of C6. So I fill in 3,000 there. So those are done. Now M4, I just need 1 of M4 for every 1 of C4. So if C4 needed 1,500, that means M4 needs 1,500. But I have 100 on hand, so it's 1,500 minus the 100 I have on hand, and that's 1,400. So because I have 100 on hand of material 4, and I only need 1,500 total, I subtract the 100, and that brings me down to 1,400. Now for M6, this is a half of unit going into every C6. So I'm going to take C6 and divide it by 2. So C6 I had 3,000 of, but I only need a half of M6 for every one of those C6s. So instead of 3,000 M6s, I only need 1,500 of M6s. So M6, I'm going to say I need 1,500, but I have 200 on hand, so I subtract those 200, and that means I only need 1,300 of M6. So I did subassembly S3, I did the 2 components that go into S3, and then I did the materials that go into each of those as well. So I'm checking those off because those are now done. We've done all those. So our last one, S4, same pattern. S4 is going into P2. I need 2,000 of P2, and I had 200 S4 on hand, so it means I need 1,800 of S4. Going into S4, I need 2 C2 and I need 1 of C8. So C8 is the easy one because it's just a 1 for 1. And if you look down here, C8 has 0 on hand. So if I need 1,800 of S4, it means I need 1,800 of C8. So that's easy. C2, I need 2 for every one. So if I need 1,800 of S4, that means I need 3,600 of C2 because I need 2 of all of those to go into one S4. So 2 times 1,800 is 3,600, and I look and I see that I don't have any on-hand inventory. So I'm just going to do 2 times 1,800, which gives me 3,600. And then finally, I've got material 2. So component 2, I need 3,600. I need 1 of material 2 to go into that. And I have 100 on hand. So for material 2, I take 3,600 minus the 100 on hand, and that's 3,500. For C8, I said that I needed 1800 of C8. That means I need 1800 of M8, and I have none on hand, so that's just 1800. So at the end of your work, you'll have a table that looks like this. And so for every subassembly, component, and material, you'll have what your order requirement would be. This is how much I would need to order. But you'll notice they're all different because they're all based on how many I already have on hand and how many of that component or material go into the subassemblies. Does that make sense? So as you do this, you start from the top down, looking at how many units you need, and then you have to consider how many each of those go into each of the following steps. And so you can't really do it from the bottom up. It's really a lot easier to do it from the top down. Any questions on that? So you're going to have something that looks exactly like this. It'll give you production requirements. It'll give you what they already had on hand. And then you'll have on-hand inventory, the tree structure, and you do exactly what we did here to fill out what the order requirement is for each of those. No questions? All right. The other thing we're doing in this chapter is our EOQ formula and our total inventory cost. And so our EOQ formula is given to us in the book on page 742. And our EOQ formula helps us to figure out Q, and we need to know that Q before we can figure out part B. So you're always going to do part A first because you need part A to figure out part B. And so as we look at this, we're being told how many total items we need. That's our annual demand. So our make to stock product is given to us in annual demand, as it says in the problem, and so that is D sub A, 250,000 units. Then it gives us the individual item cost, and that item cost is used to help calculate the holding rate, because the holding rate is with respect to the unit cost. So the holding rate, or the C sub H, is equal to the unit cost multiplied by the holding rate. So in this case, it's 10 times 0.08. And so every time you have a holding cost, you're always going to have associated with that a percentage, and you just multiply the unit cost by the holding cost percentage. So you want to make sure you convert that into a decimal format. And so math is really easy on this one, 80 cents. So the holding cost, or the C sub H, is 80 cents. The next thing it gives us is a setup cost. And the setup cost is found by looking at how long it takes to change over the equipment multiplied by the cost for that downtime. So the setup cost is all the costs associated every time we have to take the equipment down to change it over. Because anytime I'm going to take the equipment down to start a new order or do a changeover from a previous order, I have to have that downtime, and that downtime costs me money. So my setup is C, and it's sub SU. Zoom in a little bit there. So we have our annual demand is at D sub A, our holding cost is at C sub H, and our setup cost is C sub SU. And that is equal to the number of hours, 4 hours, times the dollar per hour, which is 250. And so that is equal to 1,000. So that's our setup cost. So now that we have those, we can actually calculate how many orders we want to place a year, what quantity should be ordered. And so the way we do that is we use the economic order quantity, and that tells us the amount of items we should order is equal to Q for quantity, and that is equal to the square root of 2 times the annual demand times the setup cost divided by the holding cost, and we're taking the square root of all of that. So in this case, it's the square root of 2 times 250,000 times 1,000 divided by 0.8. I actually didn't do this in advance, so give me a second while I do the math on this. And that's equal to 25,000. So Q is equal to 25,000. And this is units, by the way. 25,000 units are how many units I should order at a time. Now, really quickly, you can find out your number of orders per year because my number of orders per year is equal to my annual demand divided by my economic order quantity. So that 250,000 divided by 25,000 is 10. Math is nice and straightforward on this one. So I would order this 10 times a year based on the economic order quantity. And that is representing the break-even point where that's, if I consider how much it costs for me to set up the machine and take it down and how much it costs for me to have the inventory on hand, I'm going to order a little less than once a month, right? Now, in reality, a lot of businesses, they'll just order monthly because that makes sense to them because they set up automatic ordering, but that actually means that they're paying more in inventory costs than they have to. And so it's not, and that's why this is called the economic order quantity. This maximizes that inventory cost ratio to the setup cost associated in manufacturing. So it's balancing the two. In some places, if you don't have a lot of space for your inventory and you can't hold a lot of on-hand inventory, you may not be able to order 25,000 of a certain part. You may have to, order 10,000 at a time and order like every 2 weeks. Or you may be a place that uses just-in-time ordering. And so you're only ordering as much as you need for any given run at any given time. So economic order quantity is a great starting point. It's not always what companies use because it doesn't always make sense for their specific manufacturing philosophy. But it is a good starting point when considering how you want to move forward. So the total cost of inventory is part B. So that's part A. You can put a box around that. That is part A. So part B, I'm going to zoom back out for a minute. Part B asks for the total inventory cost. And this total inventory cost, in supply chain, we actually call it the total cost of inventory. But it's the same thing no matter what you call it. And so that is equal to the annual demand, which we were given, times the cost per piece. So that's how much the cost is for the actual unit, plus the holding cost times the amount you order divided by 2. And the reason we do that is because we're assuming that the average amount we have on hand is equal to just half of that quantity, right? Because, you know, you only have that quantity for like a day, right? And then, you know, you immediately start depleting that quantity. So my boys eat like 2 loaves of bread a week minimum. As soon as I come home with another loaf of bread, they break into that loaf of bread and they start eating it. I go to the grocery and buy another loaf. So at any given time, the amount of bread I have is basically a half loaf, because from as soon as I start buying them another loaf of bread, they're already eating it. That's kind of how inventory works when you think about it. So we're not thinking that we're just sticking it on the shelf and leaving it there to rot forever. We're thinking that we're using this inventory on an ongoing basis. So that holding cost times Q, that economic order quantity, divided by 2 is your average order on hand. Then we do the same thing where we're looking at that setup cost multiplied by the annual demand, because that's how many times we're going to have to set up, again, divided by Q. And so what is that DA over Q? That's your number of orders per year. And I'm going to take that number of orders per year and multiply it by that setup cost. So you can kind of see how they derive this equation. It makes a lot of sense, actually. So my annual demand was the 250,000, and then I'm going to multiply that by the cost per piece, which was given as 10. So that's the amount of money that I'm actually spending every year just on the materials themselves, right? Then I have the holding cost that was given to me as 0.8 multiplied by that economic order quantity of 25,000 divided by 2, because that's on average how much inventory I would have at any given time and how much it costs for me to have that on hand. And then finally, I have the number of orders per year, that DA over Q, multiplied by my setup costs. So that $1,000 multiplied by 250,000 units divided by 25,000. So that's all the numbers from this problem plugged in to the equations. And so I have 2,500,000 for my first number. And then I have that 0.8 times 25,000 divided by 2, and that's equal to 10,000. And then I have that 10 orders per year times $1,000 for every setup, so that's another 10,000. So all in all, I have $2,520,000 is my total cost of inventory. So that's how much I'm spending to buy the product, to store the product, and to run the product every time I run my machine. Does that make sense? So these two equations are in the textbook. It's 704, page 742, and your problem will be just like this. It'll give you all of those initial numbers that you need, but you have to calculate Q in part A to be able to calculate total cost in part B. And so you'll have all of that information. There's not a lot of trickery. It's really straightforward. This is a gross oversimplification of how to manage your inventory, but it gives you an idea that there's a relationship between how much it's costing me to make stuff. So if you ever had someone, I don't know how much people do this anymore, but if you ever had someone who like sold anything from their home, whether it was Tupperware or like Mary Kay Cosmetics or Lulu leggings or whatever it is, anybody who sells stuff from their home, you know, they have these parties, they have people come over and they want people to buy the product, but you can't sell what you don't have. So what does this person do? This person has to buy the product first and then resell it, and they resell it at a higher cost so that they're making a profit. But it costs them money. They have to have laid out that money first to have it in the store, on their rack, or in their house if they're selling out of their home. That costs money too. So it's really the same idea of that sunk cost of inventory balanced against, the fact that you need to have the inventory on hand if you're going to do anything to process it, to make your product. So these are just simplified ways of looking at the relationships between those costs. And with that, we're done. Those are the only two things that are in your homework. That was all the content that we had. So your homework just has those two problems again. And then on the exam, you'll see another two problems that look exactly like that, as well as problems from the previous chapter. The exam is non-cumulative, so anything that was on exam 2 means that it won't be on exam 3. Exam 3 will actually be pretty short, but I will have that open and available to you next week on Wednesday, and I'll send out a Google survey or doodle poll or something to see when you guys want to have the review for that. And if there aren't any other questions, that's it for today. Are we good? Give me a thumbs up or take yourself off mute. Thank you, Justin. Thank you, John. Good, Jeff. Trent, we good? All right. So on that note, I'm going to go ahead and end the recording, and I'll get this posted for people who couldn't be here. In the meantime, stay safe, stay healthy, and if you have any questions, please don't hesitate to reach out and contact me. All right. I will talk to you later.